Thank you very much, everybody, for giving me your time this afternoon. I'm really excited to share this presentation with you because it really does cover all of the things that make me tick academically. So my research, as Rick said, has been focused on characterising mine waste. And this is something that I started when I set my PhD down at the University of Tasmania, working at codes. I was fortunate to work alongside the AMIRA P843 GEM project. So I worked with Dr. Steve Walters and his team, looking at how we could actually use a whole range of new tools and techniques to better undertake mining mineral processing. But there was one area that perhaps wasn't immediately built into the program, and that was how we could use these tools and these data to actually predict the acid mine drainage properties of the waste and how we could actually design waste rock storage facilities to minimize geo-environmental risks. So I had this fantastic opportunity to sink my teeth into basically what was becoming quite a new area of research. So today what I'd like to talk to you about is some of the outcomes from that project, from that work, and the subsequent outcomes from my postdocs after that. So they were still at the University of Tasmania, so I'd like to acknowledge them. I'd also like to talk to you about some of the new projects we've been doing. So as Rick alluded to, I've been working very much at the front end of the mining value chain, looking at how we can predict AMD and other geo-environmental characteristics. But I've also been looking at how we can go to existing mine waste facilities and characterise those and work out if there's actually any further opportunities with that particular site. So can we actually reprocess it? Can we pull out more metals? Can we chase a whole different metal that we didn't even think of when obviously the first mining operation was undertaken? And using these tools and techniques, particularly in the mineral chemistry space, we can actually do that quite effectively. So as Rick also said, I've been working now with the GSQ, with Helen and her team. And we've undertaken some research over the past 6 months looking at sites across Queensland. So today if I get to it, because I know I do tend to talk a bit, but if I get to it, I'll give you an update on where that project's at. And I'm really excited to give you that information in subsequent seminars too. So without any further ado, let's kick off. Now, I love going to mine sites. And as much as I love looking at the open cuts, I really enjoy looking at the mine waste features. I mean, there's nobody in this webinar right now who can't tell me that image isn't stunning. And what we're looking at there is the waste rock piles at Bingham Canyon. So at Bingham Canyon, we have about 2.2 billion tonnes of waste rock on the surface. And as we can see, it's one massive challenge to manage this mine waste. We can see there's all sorts of channels here. There's many geo-environmental risks associated with obviously managing this waste. And to date, they estimate that over $400 million US has been spent on cleaning up around the mine. Now, Bingham Canyon isn't the only mine site with such a big challenge and costs being spent on mine waste. We can all probably think of many operations and sites we've been to with similar features. So we have this massive challenge. We have to move waste. We have to pay money to move the waste. We have to pay money to manage the waste. What are we doing? Are we doing enough? Are we doing it effectively? I mean, the challenge of mine waste isn't one that's going to go away. I mean, we all look at this graph from Gavin Mudd. I mean, we normally look at the declining ore grades. But what this one shows us is something on the converse. This shows us the amount of waste rock that we're actually producing. And we can see that the general trend, obviously, as we're mining bigger and bigger deposits, obviously larger tonnage, lower grade, what's the consequence? The consequence is obviously that we're producing more waste. So if we're producing more waste, we need to have robust ways to characterize it and to therefore manage it in such a way that we minimize geo-environmental risks. So, just as a take-home message, if you don't make it through the whole hour, I just want to say, as an industry, we must be better at how early life of mine geo-environmental characterization is undertaken. And so I've been fortunate, myself and my team, to be working in this space to help develop those early life of mine tools and techniques that can be used and embedded. I mean, fundamentally, what it comes down to is these things cost money. If you've got acid and metalliferous drainage, it can make mine project uneconomic and present mine owners as technically challenging and expensive long-term environmental management issues. I mean, again, I'd ask you to think about projects that you've been on where there's been AMD issues, and think about the amount of money that's been spent to try and minimize and manage that. I mean, if we could actually characterize and understand the source of the AMD and cut it there, if we spend a lot of time identifying the source and better managing that, then we can actually avoid spending these costs long after mine closure. And I guess that's a real big motivator. So let's think about how we actually predict AMD. So I like this slide because it really makes us think about, you know, how we've been doing this over time. So before the 1970s, there weren't actually formal protocols that were being used to actually predict acid mine drainage. It was quite simply coming down to looking at a rock. Has it got sulfides? Has it got carbonates? Yes, no. Let's make a bit of a qualitative observation, and let's sort of do our mine waste management and our AMD management around, you know, very qualitative observations. There wasn't really any legislation in place that said you must do it like this, you must do it like that. Here are the guidelines. But then as we move forward through time, what we saw in the 1970s, or in the late 1970s, a range of geochemical tests were introduced. These came out of North America, specifically Pennsylvania, and they were developed, I guess, with the coal industry in mind. So they weren't necessarily developed for metalliferous mines. They were developed for sort of, relatively speaking, more simple mineralogies. The sorts of things that were developed were the static tests and the kinetic tests. So if you've heard about SOBEC testing, modified SOBEC, so very chemical tests that you do in a laboratory at bench with about, let's say, 2.5 grams of sample material. Kinetic tests are a bit more involved. That's where you put some waste rock in a funnel and you irrigate it, or you do a humidity cell test. But again, very sort of simple, reasonably simple kind of tests. But they provided operators with numbers, and these numbers help them build waste models and waste management plans. And in the late 90s or the mid 90s, these were supplemented with some more geochemical tests. And now we have the net acid generation test, which basically focused on taking again 2.5 grams of material and oxidizing it with hydrogen peroxide. So this was kind of to simulate sulfide oxidation reactions. Now, I guess what you're thinking, and this is, you should be thinking this, is, well, what do we do now? I mean, this time scale, or this time not to scale rather, you know, I've shown it up to 2010. You can see it's kind of flatline there. And if we just think about all of the things we've seen in the past, you know, 15 years in terms of technological development, you know, the use of AI and machine learning algorithms, you know, the way that people have actually started to go back and look at data and pull it apart in different ways, and as I say, apply machine learning and all sorts of things. You know, where do we see that being introduced into this graph? Because currently, I guess as far as standards go and accepted practice, we're still on that flat line when it comes to geoenvironmental characterization and ARDI prediction. So that to me is a worry, and I think that's kind of the thing that's kind of triggered a lot of this this research. So again, moving forward, I think my computer's a bit slow here, so just, yep, there we go. This slide here shows something called the wheel approach to AMD prediction. And this essentially is the way in which we predict AMD. So what you can see here, there's 8 categories of tests dotted around the center. And they range from, you know, various things. We've got total metals and whole rock there. So that's where we look at sort of our geochemical data and we try and sort of do some rough calculations in terms of looking at the total sulfur, the total carbon. Can we predict acid neutralizing capacity, or can we calculate maximum potential acidity using those numbers? Then we've got the more formal acid-base accounting, which relates to the static testing that I just talked about, and the NAG testing too. Mineralogy is mentioned there, but it's used very sparingly in this kind of wheel approach. So it's only really used where we really can't resolve the behavior of a sample if it's unclassifiable or so forth. There's retention tests where we look at leaching things and seeing what sort of elements elute, you know, using different leachates, different pHs, acetic acid, or other sort of sequential extraction type approaches. And we have the lab kinetic test, where you can see a picture here in the corner there. That's basically, as I described before, where you put some crushed rock into a funnel and you periodically irrigate this to look at kind of the drainage chemistry signatures. And if you start these way before, obviously a mining project's well evolved, then you can have an idea of what the leachate chemistry might be. They're supposed to replicate field conditions. Or you can go to the effort to actually build a kinetic test. And if you go to places like the Savage River mine, you know, currently on site there, they've got 4-meter columns where they're sort of, again, trying to understand the in-field leaching behavior of some of their major waste domains that they have there. And yeah, you can also do on-site monitoring of you know, leachates and different various runoffs that you might find around the site. And the two that are mostly used are, as I said, acid-base accounting and NAG testing. These are pretty much our industry standard methods, our chemical testing methods. But at what point during when I went through that wheel approach did I tell you how to sample? At what point did I tell you about which certified reference materials to use. I mean, there's many papers you'll find, and I've contributed one myself, which kind of pull apart the way in which we predict acid mine drainage. There are lots and lots of different issues that we have in terms of, going from acid-base accounting. So I said that there were static tests, and I mentioned things like SOBEC testing and modified SOBEC testing. But if you're actually undertaking this work, which one do you use? I mean, they have different reaction times, they're done at different temperatures, they use slightly different chemicals. If there's not a routinely used certified reference material, how do you know that your NAG testing results are correct? I mean, I've worked on projects where we've had NAG pH values from 2 different labs, completely different. So which one do you trust if you're not using a CRM? This whole thing about sampling guidelines, if you've got a new project, how do you know how many samples you're supposed to be taking and characterizing by this approach? So there's lots of errors in the WIL approach, or not errors, I should say deficiencies. We could do better, and I believe that now we have many more tools that will help us get to that better place. I think one thing that really concerns me when I look at this, and I think about the different controls on sulfide oxidation. I mean, there's many different controls on what actually makes things like pyrite actually weather. We know that trace element chemistry, galvanic interactions, if you've got intrinsic fractures within the pyrite, there are lots of different things that can sort of determine whether or not that pyrite's going to react, and whether or not it's going to actually be something that's going to produce a great amount of acid in sort of sulfide oxidation reactions. But where do we capture that information in this WIL approach? So these are the sorts of things we need to think about when we need to sort of start planning to make improvements. And I think this is a really, really interesting thing. Now, what percentage of risk and uncertainty is actually acceptable in mining projects? Now, if anyone wants to chirp with an answer, absolutely, please do. But it is important. I mean, when you're thinking about mine planning, what percentage of risk is actually acceptable? Because when we look at some of the common plots, so I mentioned that, in terms of static testing, things like acid-base accounting and NAG pH testing, these are kind of the bread and butter of static tests. They're kind of the bread and butter of what you do. And this first plot here that you can see to my left, with the NAPP, which stands for net acid producing potential, that's plotted against NAG pH. And in Asia Pacific, it's quite a convention to plot your data like this. And it should stand out to you that 2 of the fields on here are uncertain. So you've got unclassified samples that are plotting in these uncertain fields. Is that acceptable? I mean, even if you look at the NAG pH and the paste pH, you can see there's a big uncertainty field there as well. So in commonly used ABA classifications, uncertainty fields can constitute as much as 50% of the plot. So is that really acceptable when we're actually thinking about mining projects and we're thinking about the waste? And the majority of what we mine is waste. So I really feel like this should sort of scream out that we need to actually supplement what we're doing with new technologies and new tests. So Q-geometallurgy. So I mentioned at the beginning, my PhD was undertaken alongside the GEM project, which was a project about geometallurgy. And so if you go rooting around for a definition of geometallurgy, I think Simon Dominy's paper in Minerals, and I've given you the link there, really good paper to actually describe and give you case studies as to where geometallurgy has actually helped improve the resilience of a mining operation. But the important bit of think about this sentence is it states that geometallurgy can minimize technical and operational risks to ultimately provide more resilient operations. So I guess what I'm trying to convey is if we can actually introduce geometallurgical tools, geometallurgical approaches into how we actually undertake waste characterization, we've got an opportunity to minimize risk and decrease that uncertainty and actually build more inert, better waste rock facilities, waste rock domains, and so forth. Often I get people ask, and it's a very, very fair thing to ask, what is the definition of geometallurgy? And so I was really happy last year when I went to the PACRIM conference and I was organising the session on geometallurgy to hear Steve Walters, who was formerly my PhD supervisor. I think he basically said there is no one fits all kind of definition for geometallurgy. So I guess it's kind of how you interpret it. It's how you interpret it. So the way that I would sort of boil down geometallurgy, I think it's basically about how you characterize your ore body using a range of tools. You've really got to know its attributes and its properties, and they will enable you to make better processing decisions to optimize recovery and profits and keep costs down. So if you actually characterize all of the mineralogical properties of your ore body, if you need to know about hardness, if you need to know about floatability, if you need to know about liberation, all of these different things, if you characterize it properly at the beginning using a range of tools, I mean, geometallurgy kind of focused on developing or identifying proxy tools to kind of supplement and support some of our more established tests. If you can do that, then you can basically make better processing decisions. If you know the hardness of your ore, if you know the amount of chlorite you've got when you're doing flotation, and that will help you optimize your recovery. It will help you, keep your energy costs manageable and so forth. So I think if we can actually take this into waste characterization, this kind of thought of characterizing properly, so instead of ore body now, we need to think about waste, then we've got a chance of doing it right. But I think the real missing thing to me in terms of how waste characterization is done is mineralogy. So I have spoken about this so many times, and I've probably written blogs and all sorts of things. One of the missing M's in AMD really is mineralogy. So when I was going through that wheel approach, I said there was 8 categories, and I said that mineralogy focused once. And as I said there, it's really used quite sparingly if we've got uncertain samples. So if we do have things that plot in those uncertain fields on that NAG plot and so forth, that's when people will go to mineralogy. And, will they go to XRD or will they do some microscopy? There's a bit of a question mark there, but it's used so sparingly, but it needs to not be. It needs to be routinely used. And I believe that if we actually routinely evaluate and, characterize, understand the mineralogy, then we have a real good shot at actually improving how we do our waste characterization. So it's not a dirty word. Sometimes when I go to meetings or I'm talking to people about their data, they present to me their geochem data. I'm like, well, where's the mineralogical data? And it's like, everyone sort of draws a sharp breath. What? It's not a dirty word. We have to be doing more mineralogy because that's the key to actually understanding our waste much better. So for me, in that geometallurgy kind of thought process, it's about embedding tools that help us actually pull out and understand mineralogy more efficiently. And how are we going to do that? Taking a step back, there are many environmental opportunities in geometallurgy focused, I guess, predominantly on mineralogy and mineral chemistry. So, across the whole mining value chain, from exploration to closure, there are opportunities to actually embed geometallurgy. So I'm going to focus on the front end. I'm going to focus in the first part of this talk on the exploration side. And what we need these tools to do, as I've obviously said, we need them to help us understand mineralogy. But we also need them to help us undertake more robust sampling. And by doing that and having sort of low-cost mineralogy tools, we will be able to characterize more of our waste zones, and we will be able to build better waste or tailings storage repositories. And again, going back to the GEM project, and I guess this is probably what stimulated my thought to, I guess, develop this environmental geometallurgy matrix. I obviously sat through many wonderful sponsors meetings when I was a PhD student and then a postdoc in the GEM project. And, at the time, perhaps I didn't quite understand it, being a young PhD student, but I remember Luke Keeney and Steve Walters, they talked a lot about the matrix approach. And I won't lie, there were a few of the matrix film jokes, which, could give or take those. But essentially, I guess what they were trying to convey was what we need to do is we need to find tools that help us get lots of information at level 1 of a matrix. So they were thinking about hardness, I think about A/B testing and bond-to-mill work index values. They wanted to find tools where they could actually look at the hardness on a lot of drill core material and use those values to kind of inform the levels going upwards. And so the thing that they landed on, and the thing that Luke did an absolutely fantastic job doing, was looking at how we could use the equative to actually understand mineral hardness. And so I guess it was probably within my first few weeks or months when I was at the BRC, I was thinking about how we could actually use this approach to explain what we're trying to do in environmental geometallurgy. So what I proposed here is the environmental geometallurgy matrix. And so basically, if you think about our static tests, they would sit at level 2. If you think about our kinetic tests, they would sit at level 3, and that's both our field and our lab kinetic tests. And basically the static tests and the kinetic tests are the things that inform the design at level 4, which is the final landform or the repository. But there's that whole bit missing with the proxy test. So I did sort of say a little while ago about the number of tests that we do. When we come to static testing, I've looked at many reports and data sets. Yeah. And you think about the size of the ore bodies that people are progressing with, the tonnages and the volumes and the masses. And the number of static tests that can be done can be something as small as 300. And you think, this bigger deposit and this few static tests, there's something missing here, there's a disconnect. And the problem is that the cost of a static test, whilst, it's probably about $50 to have the whole thing done, it's one of these things where it appears costly to people, I guess, managing the budgets. So we need to have a way that we can actually introduce these proxy tests, which sit below the static tests, which perhaps help us choose which samples we use when we're doing our static testing. So it helps us more effectively design our static testing protocol, our static testing sampling, and our kinetic trials in consequence. And that's what this matrix is really about. It's about finding those proxy tests. They need to be small scale, they need to be simple, they need to be low cost. And the thing that they really need to do is be embedded at the earliest life of mine stage. And so what do we have? What sort of tools could we use at level 1? And now I'm showing you the Enviro-geometallurgy toolkit, which you may regard as being a new wheel. So what we have here is we have 6 categories of tests. So we have handheld tools, we have simple chemical tests, we have how we could better use automated mineralogy, we've got data mining, next generation technologies, and hyperspectral mineralogy. Now, obviously, I'm not going to have time to talk about all of these, but by all means, if you're interested to know more, I'll certainly provide reference lists and, obviously, you've got my contact details so we can get in touch. But I'm going to cherry pick a couple of them. So I'm going to first talk about hyperspectral mineralogy. So here, we've done a lot of work. It was one of the tools that we first used in the GEM project. So the GEM project looked at HyLogger data in particular and how that could be used to understand alteration mineralogy and relate that to processing attributes. So how we've looked at this is looking at hyperspectral mineralogy and how we could actually look at neutralizing domains, because as we know, with HyLogger data, it's very good, and sort of all hyperspectral mineralogy data, it's very good at identifying carbonates and other silicate bases, which are our secondary neutralizers. So the opportunity we have with hyperspectral data is that it can actually help us overcome some of those challenges we face when we're doing representative sampling. So if we're scanning whole trays of drill core, we can actually understand the distribution of the carbonates and, as I say, some of the secondary silicates that participate in secondary neutralization reactions. We can actually scan vast quantities. So I've said here, Corescan, you can do up to 200 meters per day. Now, obviously, hyperspectral data can be sort of over a range in the infrared. So we've got Corescan, which looks particularly at SWIR active minerals. And we've got HyLogger data where we can also supplement that with thermal infrared. So we can actually not just look at the carbonates, but we can look at which particular carbonate is in there, which kind of supplements a bit what the Corescan can do. So what we can really do then is actually, if you've collected hyperspectral data and you're collecting that to look at alteration mapping or for whatever reason, you can actually add value to this data by performing geo-environmental domaining. And we can actually identify potentially acid forming, non-acid forming, and neutralizing domains to enable waste management, to enable and help us do that early forecasting of the geo-environmental characteristics of that material. Now, I've mentioned obviously that there's a range of IR responses, and this table by Paul Linton really sort of captures which are good and which are bad under different ranges of infrared. So we can see, obviously, for the carbonates, calcite is good in both SWIR and thermal infrared carbonates. We can also see that, our sulfides are non-diagnostic in both. So we need to actually think about how we can tease out the data on the sulfides from some of the other pieces of information that these instruments spit out, which I'll talk about in a couple of slides' time. But this is basically, it's quite a good summary in terms of understanding which minerals are active and which are not. So what we did was, thinking about that particular activity, we had an opportunity. Laura Jackson was a PhD student of mine, recently submitted. She was working down at the University of Tasmania with codes, and supported by Preston Corescan. And what we did was, in the material she was looking at, we scanned a whole bunch of material, and we created something called the Geo-Environmental Domaining Index. And so what we did there was we calculated the mineral abundance, and we took stoichiometric neutralizing potential values and acid potential values as well. And we multiplied the calculated mineral abundance by the stoichiometric MP or AP values, and we also multiplied that by the relative reactivity values. And these were published values from Sverdrup of the relative reactivity of different minerals at pH 5. And what that did was, that gave us a value, and that value is our GDI, or our Geo-Environmental Domain Index value. So I guess as an example, this works pixel by pixel. So if you take a pixel like this in this example, chlorite 60% match, carbonate 30, quartz 10, you multiply those values, and basically for each of these, you get basically a GDI pixel value. And for each of the three minerals it's spat out here, we total those to give us basically a rounded pixel GDI of 30. So what does 30 mean? It's a unitless number. So, you know, is that good or bad? Very good question, is it good or bad? So we had a whole big data set. We did XRD, we did static testing, we did a whole bunch of different ways to characterize this to come up with some sort of way that we can make these values actually mean something. So what we did was, we assigned these GDI risk weights. So you can see they range from extreme risk. So if you've got a negative value, this basically suggests that you've got no primary neutralizers, you've got a dominance of acid-forming minerals, and these are rocks to watch out for. If you've got, in terms of AMD potential, I should say, if you've got things that were sort of very high numbers, so 40,000 to 100,000, very low risk, what this means is that you've got carbonate dominating as the first mineral that Corescan identified, and that in terms of acid neutralizing capacity, you've got an abundance of it, it's effective, and it's likely you'll have a long-term ANC situation going on. So with these 5 categories, we were able to do something useful with the Corescan data. And if you want some proof, here's a couple of examples. So this is a sample that we got from a skarn zone of a particular deposit. And I'm showing you here the core photography, and I'm showing you the Corescan classified mineral map. Now, Corescan now has a sulfide mask that you can request to be switched on. So basically, using the RGB image processing, sort of married up with some of the spectral features, they can actually do sulfide recognition. And this is something that we used in the GDI version 2, which is the data that I'm showing you here. So with this particular sample, we can see that we've got a high abundance of carbonate identified in the classified mineral map, which you can see in the 4th image there. The GDI score here for this particular sample was about 34,000. So it's classified as low risk. And so, as I said, we did some validation testing. So our static testing here shows us on this dashboard that this sample is non-acid forming. You can see that underneath each of the various graphs, it says NAF many times. So our static testing classification is that it's non-acid forming. So what this is basically saying to us is that the GDI version 2 did a very good job at pulling out that this was a low risk sample. Well, you might think, well, that's easy. It's you know, it's carbonate rich. Well, fair enough, but you know, there's some evidence. If we look at another sample from this particular skarn zone, we can see here a little bit of sulfide starting to be recognized there. And the carbonate that has been identified is concentrated along this vein. So the GDI value it was given was just under 2,000, which classified it as potential risk. And if we look at the dashboard here, what we can see is, for the most part, you know, a lot of the graphs, you know, they sort of suggest that this is a non-acid forming sample. But if we look at the sulfide sulfur, we can see that actually that's quite high. And I guess what this is alluding to is that in the short term, this might be a non-acid forming sample. But once that acid neutralizing capacity has been consumed, then we've got the potential to have something that's going to generate acid longer term. So the fact that the GDI recognises as potential risk is a good thing. It's flagging that it's not a problem now, but it could be a problem a long term into the future. And if we look at a final sample from the potassic zone, what we have here, if you look at the sulfide recognition image, you can see there are speckles of white there. There's quite a few speckles, and we can see that actually the pyrite in this particular sample is somewhat associated with the sericite. Can't see any carbonate in this sample whatsoever, and the GDI has correctly identified this as a negative number sample with a high risk. And if we go to our geoenvironmental dashboard, what we can see is that by all the different plots, it is indeed classified on the top row as an acid forming to potential acid forming sample. So our static testing confirms that this is a high risk sample. So really what we could do is actually just, if we've got the data, if we've got the Corescan information, we can plug it into this and we can actually tease out these GDI values to help us actually choose which samples, if indeed we've got a limited number of samples we can choose when static testing, this will actually help us inform that design of sample selection. Not to bias our samples, but to better inform us. So it will help us not bias towards one particular domain, it will help us actually domain on a broader scale and then choose a representative number of samples from each of those waste domains based on the GDI values. Now, I have said that GDI values are unitless. So you might think, well, you know, in all those other plots you showed me, there were two things that were plotted. You know, it was NAT versus NAG, it was NAG pH versus paste pH. So what can we plot the GDI against? And that was something we thought about. And, you know, why not sulfur values? I mean, most mine sites, you know, their geological database will have sulfur values. So if you've got Corescan or other sorts of data, plug it into these algorithms and plot it against the sulfur, and then you can start doing some really early waste forecasting. So we, you know, here what we've come up with are 5 classes and one very thin anomalous zone. If anything goes in there, things have really screwed up. So this isn't uncertain, this is telling you there's an error and you need to go and do something else, or you need to really look at those rocks properly. And, you know, you can see things here could be plotting as pack waste, so prioritised for static testing, or they could be nominated to actually have some good mineral chemistry done there. So if you've got sulfides and they're going to deport to your waste, why don't you characterise it using mineral chemistry tools and figure out if you've actually got a different commodity in there? And then, you know, you're actually turning your waste into something useful. I mean, there's lots of potential things you could do. Where you've got NAF inert material there in class 4, perhaps this is material that'd be ideal to use as inert waste rock layers, as road base on dam wall lifts, etc. So we're thinking about how we can use this waste and actually engineer it better around the mine site. So it's gone from a low value to no value material to actually something that's usable and reduces the volume of waste you have in your piles, like the thing in Kenya. So some of this data, obviously, I haven't got time to really go into the guts of each of these different things I've talked about, and there is more. If you are interested to read a bit more, there's a couple of peer-reviewed conference papers that Laura's put out, and they're available through the UTAS website if you request a copy. And now that the dust has settled a bit from Laura's submission last week, I'm really keen for her to write up one of her, I think it's going to be one of her key papers from her thesis, where she actually looked at scanning the material that went into a kinetic cell using Corescan and used this bulk mineralogy data to actually understand the leachate chemistry coming out of the kinetic trials, because sometimes that can be a really hard thing to do. You've been running a kinetic trial for 6 months, you haven't seen any reaction, your pH value hasn't really sort of declined or gone upwards. So is it a dead cell? Do you call time on it? Or is it just that the mineral reactions are quite slow and you need to give it another year or so to run? So by doing the column feed characterization step that Laura's done, and a couple of other things that we've developed on the site too, it's actually possible to understand your kinetic cells and that leachate data much more effectively. So really a lot of things can be done with that data. And similarly, some of you might be thinking, well, I don't have access to Corescan, I use a HyLogger. So we actually have a similar index that we've developed using HyLogger data, which we call the HyGI. And it basically works in a very similar way to the geoenvironmental domaining index. So we have neutralizing potential values and we multiply those by the relative reactivity to give the standard value. And then we look at sort of the HyLogger intensity values that are spat out. And basically we multiply those and we get a mineral value, and then we sum those to give us our final HyGI score. And so we tried this at a porphyry mine site up in northern Sweden. And again, I haven't got time to go into the details of it, but it is published in this paper with the link given there. And what we were able to do here was, again, to actually come up with waste classes using the HyGI information, the total sulfur, and we also supplemented that with another piece of information, the acid rock drainage index values that we created. And so basically what I'm trying to say is that There are many things we could do with this data. So if you've got it and you're curious to try it, why not? We've got things that you can plug it into. Let's see if we can actually use these effectively at level 1 of the matrix. Now, again, I've shot myself in the foot a bit with time, but we'll keep forging onwards as best we can. I've also mentioned at level 1, there are many tools. So I showed you the new wheel. So I just wanted to sort of touch on some of the other things that we have been using a bit more routinely. So environmental logging, that pertains to the to the acid rock drainage index that I mentioned in the last slide. But there's other really simple things we can do in the core shed too. We could use chemical stains. We could actually use the equitip that Luke Keeney spent his PhD researching and describing uses for. We can use a range of new handheld technologies. So I put here portable XRF. That's obviously becoming a bit outdated now, and it's more routinely used, I should say, not outdated. But you know, we can supplement the use of that with things such as LIBS technology. We can use UV. In Laura's PhD, we actually looked at how we could use ultraviolet to identify carbonates and to see if that could inform, I guess, some of the carbonate and the neutralizing potential domaining we were doing. A whole bunch of stuff. So what I'm going to do is I'm just going to choose a couple of those to talk about in the next couple of slides. So the acid rock drainage index. This is a logging code that we developed many years ago, so 2011 now. And basically what we do is everyone's done logging, we all log, but how many times do we actually log in terms of thinking about acid rock drainage? Not many, I'm going to imagine. I did a lit review and that was kind of what I came out with. Not many formal codes exist for this. So what we were trying to do was to introduce some sort of formal code. So basically we log by 5 different parameters and we rank those parameters, and then basically we sum it, and the higher the number, the more acid forming the sample is. Now you might be thinking, well, that's a bit biased sampling to just do something that's the size of a grain size kind of card that you keep in your wallet or credit card. That's true. So this paper by Cornelius, one of my old students, Rebecca Cornelius, who's now working in WA, one piece of work she did during her honours was looking at how we could actually make that more of a useful tool in the core shed. So she came up with a modified ARDI that introduced the interval index assessment as well. So again, that's detailed in Rebecca's paper, so I'd urge you to go and have a look at that, or to talk to me a bit more about if you want some more information on that. But that's a really useful way to actually start getting some early numbers into your database in terms of ARD potential. The equitip, obviously this spits out hardness numbers in the leads, that's the unit. So here we were trying to think about rate of weathering relative to other pieces of data that we had. So here we had the opportunity to look at drill core material from Ernest Henry, and we also looked at some material from the west coast of Tasmania, copper mines Tasmania. And that's actually where this is from. But here what we were able to do was we looked at the total sulfur, we did some simple paste pH testing, and we used the mineral hardness as well to actually start domaining acid forming and non-acid forming domains. And we did this and we validated it with mineralogy and with aesthetic testing data. We found that, again, this was quite an effective way to collect data in the core shed. And, you know, if you've got, you know, paste pH tests are a really simple thing to do. If you've got a bit of money where you can use the pulse and do paste pH testing, you've got your total sulfur value, collect that leads value as well in the core shed, and you've got a real opportunity here to do some really low cost early domains. So big tip in at level 1. I talked about staining, and I'm sure we've all, you know, had those lovely lectures when we were undergrads where we stained lots of thin sections to think about sedimentary petrology and all sorts. Well, you know, Murray Hitzman wrote this great paper, I think it was in the late 90s, where he talked about staining drill core materials. And I haven't seen many papers since actually on this very thing. But when we're thinking about neutralizing potential, if you haven't got the ability to use Corescan, why not just go back to basics and do chemical staining, because it works. So what we did was, again, in some of the projects based down on sites in Tassie, stained our drill core using alizarin red S and an organic dye and potassium percyanide. Obviously, we used hydrochloric acid to mix those up in, painted the core, and we looked at the staining responses. So we also HyLogged these, but obviously it spat out the image, which we looked at, the stained image. And we can see, in terms of acid neutralizing capacity for this particular thing, there's a high ANC sample there. And what you can see there is the staining response for that high ANC sample. Pink pink is good, pink suggests calcite. So we looked at the XRD, we did some XRD work on that, and indeed, this wasn't a false positive, this was indeed a calcite-dominated sample. And in terms of, you know, was the XRD correct, we then further validated using the probe, is indeed calcite. So if we can't get to a Corescan instrument, you know, we want to look at, you know, a lot of drill core, and we're not sort of, and there's lots of different white minerals in there. You're not confident that your loggers have actually picked up the carbonates properly. You can stain and really effectively see that. So again, it's another tool you can use at level 1, super simple. Now, there are ways that we can improve the use of automated mineralogy too. I probably don't have time to go into this one, but just to say that if you do have MLA data, we can actually plug it into something called the computed acid rock drainage risk ratio protocol. So basically what we do is we take X mode data. So if for example, you're doing flotation test work and you're looking at your ore phases and you're not really so much thinking about, I mean, you're looking at the tailings in terms of thinking about how much of your ore minerals you've lost, that you haven't recovered. Well, how about plugging it into this to think about what those future tailings might be like once they're deposited? Are they high risk tailings, are they low risk tailings? We can do that. We can take the X mode data, we can use eCognition, an image processing software, which is, I guess, mostly used by the medical industry. We can take that classified dot, we can grow it out to, we can overlay it with the BSE image, grow out the color to the mineral phase, as it were, the classified color. And we can actually start working out the surface area really quickly. And with that surface area, we can again think about relative reactivity and acid producing and neutralizing potential values, ratio those and come out with a card risk ratio. So if you've already done your flotation test work, and you've already done your MLA work or sort of other automated mineralogy technique, you've got the data already, so you can plug it into something like this and you can start understanding the ARD characteristics of your tailings. Super simple. So we have all these, you know, these opportunities with this data. We just have to think about what to do with them. And one of the great things about being alive right now and a researcher right now, obviously not COVID, but one of the great things is data mining and machine learning. So we've got all of these fantastic tools out there that can actually help us look at these data sets and think about how we could optimize the use of this data in this particular context. So I've, you know, work that we did with Matt Cracknell just before I left UTAS, came up with something called the Automated Acid Rock Drainage Index. So I'm sure many of you out there were thinking, that's great, you could log, you could do your ARDI and you could completely mislog something, or your ranking of, you know, sulfide abundance could be completely different to the next core logger's abundance. That's very true, and we're very aware of that. And using some of these tools, we came up with an automated way to do the acid rock drainage index. So again, that's a paper that's available, Minerals, the Geometallurgy special issue. So I urge you to have a look at that if you're interested in that sort of approach. You know, there's opportunities to look at the assay data more effectively. So Laura Jackson, in her new role with RGS, she presented last year at PACRIM ways that they were using the calcium and the magnesium to do that early neutralizing potential domains. They were using those values and they calibrated it with some static data. And they looked at sort of, I guess, working out the dolomite and the calcite abundances to actually help them actually better design or better design their waste schedule. They're doing waste planning. They wanted to improve their scheduling. Other ways, you're going to hear about this, I think, from Angela and the team down at the codes as well in some of these future seminars. But they looked at calculating ARD using, no, sorry, they looked at, they're focused on calculating mineralogy from assays. So in some work that we did before that with Ron Berry, and we presented that at ICARD in 2015, we did the calculated mineralogy approach, but we took it that one step further where we actually calculated ARD. So again, if you've already got the data available, you haven't needed to actually really do much to actually start understanding the ARD characteristics of your deposit. And subsequently, there's been a couple of more conference papers from different groups there who are also taking this approach, which is really great to see. So there's lots of exciting opportunities out there in terms of what we can do. And you know, there's even more than I could possibly talk about. So in a couple of seminars time, you'll hear about some of these new technologies from Nathan Fox. And again, you know, we're starting to understand what these technologies can do in terms of telling us about alteration mineralogy or the genetics of an ore deposit. But why don't we take the time to also look at how we can use these data to perhaps do the automated ARDI in 3D? You know, there's all sorts of things we can do. So, you know, that's the sort of work that we're going to be focusing on at the BRC in the next few weeks, months, years. So that feels like that was an entire talk in itself, which it was, but there's just a little bit more for anybody who's still hanging in there. Now I'm going to tell you about some of the work we're doing with the GSQ, which is focused really on looking at historic mine sites in Queensland. So anyone who was at Digging Deep would have seen me sort of introduce this. So I guess the work that we're doing with the GSQ is focused on a few different big challenges that we've got right now. So obviously Australia's got a critical minerals strategy. We know there's a global demand for critical metals. We know that the social license to operate is a big deal. It always has been, but it's definitely become a bit more centre stage after some of the recent disasters we've had internationally. And I'm talking about Brumadinho, of course. But, you know, more local scale, I mean, you know, it's every year or so or every few months, you know, there might be an article in the ABC talking about this mine site and that mine site across Australia with this AMD issue or so forth. So we know that mine waste management is something that's on the public's mind. But we've also got this other thing going on, which is the circular economy. And a few years ago at the World Economic Forum, it was stated that Australia would become a $26 billion industry by 2025. So we've got all of these things going on. How are we going to bring this all together into one solution? What can we do? So this is kind of, I guess, the impetus for this project that we're doing. So what we're looking at really is critical metal exploration and mine waste, abandoned and operational sites. Let's explore what's in that waste. Let's see if we've got critical metals. Let's reuse it. So we're thinking circular economy, and it will minimise the environmental risks. So we won't see these articles pop up in the ABC and so forth in the future, because we'll be doing a better job in terms of our A&D management. So again, anyone who was at Digging Deeper would have seen me talk about this sort of thing we've been doing in Tasmania. So I'm not going to talk about it here. But in Tassie, there has been a few sites where mine waste has been looked at sort of as an economic prospect. And we developed a geometric characterization approach to characterizing the mine waste. And again, there's a link there to a paper of our study at the old tailings dam. So if you're interested, please read that. But this is kind of where this new project has kind of stemmed from. So what we've been doing is we've been going around to different sites in Queensland. So anybody who's LinkedIn with me would have seen me posting kind of summaries of some of these great trips we had. And they were great and they were fantastic. It was so good to go and have a look at mine waste in this day. Really excited me. So there's a map there showing some of the sites that we've had the opportunity to obtain samples from. And what we're doing really is we're looking at, you know, we're doing a first pass geomet investigation. So we've done multi-element geochemistry and we're about to start our next phase of work, which is looking at the mineralogy and mineral chemistry in a lot of detail. And so there's the sites, there's the waste types that we've sampled and the target elements that we're looking for and the number of samples that we've collected. So just as a quick kind of like, you know, given that you've hung in there, let's just have some nice pictures to bring it home. So this is basically showing you the sorts of things that we've sampled. So at Capricorn Copper, guys on site, they were absolutely brilliant to help us access the samples and host us. And we were able to collect a broad range of tailing samples across the dam and waste rock materials too. And we've just got the geochem results back from there. So we're going to start having a look at what the cobalt content actually is in those materials. We also had the opportunity to collect some drill core. And so what I'm showing you here is some micro XRF mapping we did with Anthony and the team at the CMLR and Lachlan Casey at the UQ microscopy lab. And what you can see here is, you know, I guess when I started this work, I thought cobalt's going to be cobaltite, or it's going to be cobaltiferous pyrite. But what you can actually see here is the cobalt's actually rimming the pyrite in some sort of carbonaceous phase. So this is, you know, this is pretty interesting stuff. So when we do our laser ablation study on this, we'll be able to really investigate what actually is the main host of cobalt in this material. At Lady Annie, we were able to sample bench 1 and bench 3 at pads 2 to 14, as you can see here. And we were also able to sample some of the waste rock in the bottom sort of middle picture that you can see there. And the waste rock here really, you know, when you went to go and have a look at it, you could see it was packed with chalcopyrite and all sorts of other copper sulfide phases. So it's going to be interesting to see where the cobalt's hosted there. At Wolfram Camp, here we had the opportunity to sample tailings and waste rock. So we've got a couple of projects here. So in that top Google Earth image there, the things in blue are from a concurrent study that's occurring at the SMI2, but with a slightly different group of researchers. But our samples that we collected with Dominic Brown earlier in the year, shown in green there. So again, here we're chasing tungsten, and we can see when we're walking around the site, you know, there's a packed cell, we've got really sooty sulfides, got molybdenite everywhere. So it's going to be quite interesting to have a look at those numbers. And at Baal Gammon again, this is a really interesting site because it's currently back in its abandoned mine status. So the DNRMA are currently sort of managing the site. You can see that the cover that's put down in some areas has opened up, which was good for us because it meant we could sample the material. And boy, oh boy, these rocks were pretty. Very heavy, which Dominic will remember because I made him carry them around. Thank you, Dominic. But chockers full of sulfides. Well, we've got massive arsenopyrite, pyrrhotite, and the numbers from this site, in terms of looking at indium, they're going to be really, really good numbers. Mount Oxide, again, we had an opportunity to sample the waste rock. You can see in the aerial image there, you can see these kind of really steep escarpments next to the pit lake there, really sooty magnetite, and it's a very sort of ferruginous waste rock kind of place. But as you move out from the site more towards where you can see MOWR36 on the Google Earth map, you have these small piles of waste rock where we've got lots of obvious copper oxides sitting on the surface. Pandora was another site we got to look at, very small operations here, but again, lots to see in terms of heap leach material and waste rock material too. So where are we at with the project? Because I do get asked this a lot, and I'm sure Helen will be happy to hear this, that we've had the chemical assay data come in today. So I didn't have time to sort of put it together and share it with you, but hopefully in a later webinar, I'll be able to share that information with you. But, opening my emails earlier today, it was like Christmas. I was so happy to see the data there, and I could see it's definitely interesting. So very happy to get my teeth sunk into that. And now the next plans are to start the XRD program and to continue on with the MLA work and start getting the samples down south for laser ablation ICP-MS. And by June, we'll have our final reports as to where the critical metals or the new economy metals are sitting in these materials. And this information will help us understand how we actually process these materials to recover them. So this is all thinking about first pass geometallurgy, because this is going to inform us as to how we could actually recover these new economy metals down the track. So I guess bringing it all back together, if we can think about early life of mine, I showed you this and I said, what are we doing in 2020? And I hope we can all agree that motivated by a whole bunch of different triggers, technology explosion, ESG factors, and the opportunities we have with machine learning, we can see that we have this really great opportunity to improve how AMD risks are predicted. It's long overdue. We've now got tools and technologies, and we can use geomet approaches to actually do a much better job. So going forward, definitely want to see more of this happening, and I'm certainly going to be doing it myself. But there's more things we could do with this data that we haven't even really thought of yet. So, I mean, we've got all this information on silicates. We can start thinking about developing greenhouse gas consumption indexes. We could look at predictive dust characterization protocols. We could even, scan heap leach materials and actually get some bulk mineralogy on that. So there's lots of more things we could do with these technologies in other geo-environmental areas other than acid mine drainage and waste rock management. We've got to start doing them. And in terms of looking at end of mine life or operational mine sites, lots more things we could do during operations and post-closure. I mean, let's characterize the waste. We could actually reduce our long-term liabilities much more effectively. We could have opportunities for economic rehabilitation. We've seen it at New Century Mine, other sites down in Tassie. There could be so many more projects like this in Australia. And I think now's a really, really good time to be getting our teeth sunk into actually having an opportunity to do that. So with the DNRMA, with GSQ, we've got a lot more work to do in the next few years, and I'm pretty excited to be doing it with Helen and the team. So on that note, at 4:30 exactly, I may add, so I haven't got over time, I would like to thank you for your attention, and I'd like to acknowledge all of these people stated on this slide. So thank you very much for listening.